Greetings and salutations. Welcome back to the Everything Astronomy podcast. Today, Tom and I are joined by Professor Gültekin from the Astronomy Department at Michigan. He graduated from UPenn and then went on to get his PhD at the University of Maryland and came to Michigan for his postdoc. He's now an assistant professor in the Astronomy Department and actually taught all four of us Astro 201, Introduction to Astrophysics. Today, we'll be talking about Professor Gültekin's background, how he got involved with black hole research, and why black hole research is such an important field of study. Professor Gültekin, welcome to the show. Thank you for being here.
Thank you for having me here.
Awesome. So our first question is about the field of black holes. And so black holes have grabbed the imagination of and the attention of many people around the world because of big sort of media breaks. So there was a picture of the black hole, there was the movie Interstellar, but now there was also the Nobel Prize and also the work of Stephen Hawking. And black holes have now kind of broken their way into popular culture. And so how did you start to develop an interest in them professionally?
Professionally, it started in grad school. I was always interested in black holes for as long as I knew what they were. In fact, Stephen Hawking and Brief History of Time is what first got me interested in astrophysics. In particular, I always was interested in science, but Brief History of Time got me interested in astrophysics and black holes in particular. So I started working on black hole stuff in grad school and have stuck with it since then.
Did you have an inkling that you would be doing that from undergrad, or was that something that, because most undergrads I think don't really reach a good enough level of math and of just knowledge to be able to say I'm pretty definite about studying black holes. So was that something that was in your mind when you decided to go to grad school, or did you develop that interest once you got there?
No, I actually so when I was an undergrad, I did research with David Kerner, who's now at Northern Arizona University. And the research that I was doing with him was on star and planet formation stuff and circumstellar disks kind of stuff. And I really enjoyed that work, and there was and still is a future in that kind of work as well. So it was, I saw it as a growth opportunity, and that was my first chance of doing research, and I liked it and thought I could continue doing it. So I started so I went to grad school thinking I was going to work on that kind of stuff, planet formation in particular. And so I did that for my first 2 years of grad school at Maryland, and then decided to change things up and kind of work on a research project that was closer to my first love, and was happier for it.
And now it sounds like a lot of people are studying black holes from all sorts of different backgrounds and different approaches, and it's very popular. But at the time, I would assume that it was much less so. Was it a field that was already pretty established as you went into it, or was it really a field that was starting to grow fast?
It was pretty established then. So so black holes were first theorized or just as a theoretical novelty as solutions to Einstein's equations, in the early 1900s. But since the 70s, they have long been suspected to actually exist. And, depending on exactly when you say that, there was no sort of eureka moment. There was just sort of a growing consensus that actually, no, these X-ray bright objects that we see are probably powered by black holes, and sort of just kind of a growing consensus of that. So there has been long work even before we were positive that black holes existed, that on work of stuff that is powered by black holes, and that. So it was pretty established, but there's lots of stuff to learn about it. And so that is part of it. I mean, in particular, gravitational waves had not yet been detected directly. They had been seen to be emitted, and the LIGO was being worked on, but they hadn't been detected at the time. So it's among the things that I saw as growth potential in an area of research.
Mm-hmm. So then, given that black holes as a research topic was already established, what specifically did you want to study about black holes once you made that transition in grad school?
So what I first worked on was theoretical analysis or numerical simulations to try to understand a class of black holes called intermediate mass black holes. And we, together with my advisor, Cole Miller, and collaborator, Doug Hamilton, we looked at how you could build intermediate mass black holes from smaller stellar mass black holes. So at that point, stellar mass black holes were known to exist. And supermassive black holes were known to exist. And so stellar mass black holes are things that are the end result of stellar evolution from massive stars, and thought to give you black holes of masses, tens of solar masses, tens, of times the mass of the sun. And supermassive black holes, although we're not certain how they're formed, there are a number of ideas, but they're definitely not formed in the same way that stellar mass black holes, or they certainly don't evolve the same way. And those have masses of, 100,000, a million solar masses, up to a billion or 10 billion solar masses. But there were new observations that were leading us to suspect that that there was an in-between class of black holes that are called intermediate mass black holes. So they're somewhere in between. They can't be either of them. And so we were looking at whether you could form these intermediate mass black holes and, say, make 1,000 solar mass black hole from repeatedly merging stellar mass black holes. And we were trying to do it in a dense stellar system like a superstar cluster.
Mm-hmm.
And so maybe something that we should have done, or something we should have asked you before we asked you that, was why is it that people study black holes? Because they are surely interesting, and it's a cool idea. But why are they more important than just a cool factoid about science? Why are they seemingly such a big focal point in physics and astronomy?
So don't underestimate the coolness factor in when wanting to study it. We're all humans, and we're all get dazzled by dazzling things. So that I'm not going to say that's not part of it. So there are a number of reasons people are interested in black holes. From a physics perspective, it's as strong as gravity can get. You're making an object as dense as possible, and so our best chance of understanding general relativity, in particular testing general relativity, is from extreme objects like black holes. So that's one perspective. From an astrophysicist's perspective, they are also the black holes that I study are supermassive black holes, and they have a connection to galaxy evolution that is not completely understood. The mass of a black hole and the size of a galaxy, measured in a number of different ways, are linked more tightly than we might otherwise expect, which tells us that something interesting is going on. So just empirically, when you look at the masses of black holes as a function of the mass of the host galaxy, or a kinematic measure of the size of the galaxy. They are very tightly coupled, which is surprising given how physically small a black hole is, even a supermassive black hole, compared to the galaxy. It's a colleague of mine, Professor Eric Bell at University of Michigan, said that it's sort of like how, if a golf ball in the center of Ann Arbor, the size of the golf ball in Ann Arbor was related to the temperature of the city of Ann Arbor. It's why is something so small relating to something so large? You would think to find big black holes and big galaxies. That's not the surprising thing. The surprising thing is that if you tell me the mass of a galaxy, I can tell you the mass of its central black hole. So something is going on in the evolution of these two things that's common and that joins them. And that will help us understand both the growth of black holes and the evolution of galaxies as well. Smaller black holes, like stellar mass black holes, are interesting for understanding, the end product of stellar evolution. Type 2 supernova are some of the brightest objects, and so they're interesting, and extreme events in general tell you about the limits of our understanding of physics, right? When the further to the right you go on a graph, no matter what it is, the more you're stressing our understanding of physics, whatever that is, and it tells us something about what's going on and whether we're right or whether we have to modify our understanding of any of the number of things that go into to any of these astrophysical.
And to hit back on the idea of the golf ball in the middle of Ann Arbor dictating what temperature the rest of Ann Arbor would be at. What are there leading theories about that? Because I mean, I was unaware of that, and that's really cool.
Yeah. So we don't know whether it's the golf ball determining the temperature or the temperature determining the size of the golf ball. So let me go away from the analogy. The mass of a central black hole is very closely related, or closely empirically related, to the velocity dispersion of the stars in the bulge of a galaxy, or the spheroidal component of a galaxy. So the velocity dispersion is the range of velocities that you see. It's measured in line of sight, but we do our best to get as much 3D information that we can for these things. And so the random motions of these stars, or the kinematic properties of the stars in this galaxy, are very closely related to the mass of that black hole. We don't know whether the velocities of the stars are, quasi-directly leading to the mass of the black hole, or the mass of the black hole is quasi-leading to the velocity dispersion of the stars, or whether there's, a third, common factor that is doing it. One of the leading ideas is an idea of self-regulated feedback. And in this idea, when galaxies merge, the stars get all kicked up and move around, but you also have torques on the gas in the galaxy. And so those torques on the gas can, wrench the gas towards the center of the galaxies, of the merging product. This cold gas does two things. One, it feeds the black hole at the center of the galaxy, and that grows the black hole. The other thing cold gas does in astrophysics is it forms stars. So now we're forming stars and moving those stars around as well in this round part of the galaxy that we think is important for, importantly related to the merger of these two galaxies. So an accreting black hole, when a black hole is accreting the gas and holding onto it, it also powers outflows, both winds and jets. if those outflows from these black holes can couple to the interstellar medium, to the gas in these galaxies, if it can couple efficiently, there is plenty of energy to heat up and or expel all that gas from the galaxy. And so if you've heated up or kicked out all the cold gas from the galaxy, you no longer can feed the black hole, so it doesn't grow anymore, and you can no longer create more stars that are creating this galaxy potential in the spheroid component that is what the velocity dispersion matches. So the same thing that introduced the growth of the mass of the black hole is the same thing that can, sort of create the stars that we see in this component, and it's the same thing that is shutting it off both of those things. So that's one leading idea. Another idea is that very similar thing happens, but it's not the black hole's outflows that are doing the heating and or expelling of the gas from the galaxy. It's the supernova from these stars that are being formed that are heating up and or expelling the gas from the galaxy, and that's what's doing it. So those are very closely related, but it's still hotly debated whether one or the other or either is the prime cause of what's going on here.
Is this question something that you study directly, or is it just something in black holes that you happen to know about because it's in your field, but not something that you work on directly?
So I work on it kind of directly in the sense that I do a lot in measuring black hole masses. So this relationship between black hole masses and velocity dispersions, which was, first discovered by Carl Gebhardt in 2000, is something that I have advanced as well in collaboration with Carl Gebhardt and many others, including Doug Richstone, who's the one who hired me at Michigan originally to work on this kind of stuff. So I've measured quite a few black hole masses. I have done a statistical analysis to really understand these relationships between the black hole mass and the host galaxy properties, not just velocity dispersion, but also the bulge luminosity and so on. So I'm interested in that, and so from an observational point of view, I'm very interested in what the answer is. I don't know what it is, but I'm very interested in it, and making sure that any of the theoretical ideas are tied, have to match the data as closely as possible.
And so we all saw, many people will have seen the picture of the black hole that was taken. And, by what they tell us, that was immensely difficult to take, and it's not very precise. So how are you able to make measurements on black holes if black holes are so hard to see and so far away and relatively so small?
Yeah, so their mass is shown to us through gravity. So there are a number of ways that people do this. The way I do it is through a technique called stellar kinematic or stellar dynamical mass estimation. And what you do is you take pictures of galaxies and you take spectra of galaxies. And the pictures of galaxies tell you how the starlight is distributed. And the starlight, how the starlight is distributed tells you, with some assumptions about geometry, tells you about the mass within the galaxy due to stars. The spectra tell you about the velocity, the line of sight velocity of the stars, and we come up with a mass model of the galaxy that includes the stellar component, a dark matter component, and a black hole component. So if we can look really, really close at the center of the galaxy, we'll see excess motions in the stars close to the black hole. And when we look at if there is a black hole there, and we can measure the amount of excess motions that we above what you'd get if there were no black hole there. So we're modeling the entire galaxy to to see what component of mass there is at the very center that we don't see in the light, because we've measured the light, so we know how much mass there is due to stars there. And the excess mass, in a sense, we attribute to a black hole there.
Right.
And
So it sounds like there's a lot of the observations that you take are, are subsequently give you lots of data and lots of numbers that you then have to analyze and build models for and simulate and all of that. But when people think of, physicists, or I think astronomers as well, they're not thinking, I don't think that the first assumption is, oh, it's a lot of number crunching and a lot of doing numbers. I think most people think it's equations on a blackboard. And that's definitely a big part of, for example, the undergraduate curriculum. There's a huge, most of it is studying equations on a blackboard, and there's not so much computer/number stuff. How did you get to learn, or how do you learn, or how'd you get exposed or start doing all of this big data, number analysis, simulation business?
So my first exposure to any sort of computer programming was in high school. I did not sign up for a computer programming class in high school, but the class I signed up for didn't work with my schedule, and they put me into the computer programming class anyway, just to fill out my schedule. So it worked out well. I actually, the language that I learned there was Pascal, and I have never touched that since, but the principles were important there. So when I started doing research as an undergrad, there were two things. One project I did was mostly sort of web, I wouldn't call it development, web page tinkering is what I did, which got me comfortable with command line interface, because that was all that was really available to me at the time. And then for my junior and senior year, working with David Kerner, was when I started doing real Fortran programming to model a circumstellar disk. And so other than that initial high school class, I am largely self-taught. I did take numerical astrophysics class in grad school and some other sort of scientific computing class as well. But mostly it was, here's a code, start tinkering with it to see what happens. And it's something that I am comfortable typing on a keyboard, and so I'm okay doing it. It was a good way to learn. So that's how I did it. More and more, we're recognizing that people with my background in computing write awful, terrible, mangled, ugly-looking code. And so more and more, we are asking our undergrads and our grad students to take more formal computer classes, computing classes, computer language classes, in order to develop their skills, and so that the codes run as efficiently as possible, and more importantly, are maintainable as well. Because a lot of times these things are million line codes that 100 people are working on to work together to get something to work properly, and so you need the code base to be as good as possible.
Is coding and computer programming and all of that a big part of what you do now? Is that even maybe one of the biggest things that you do on a day-to-day basis for your research?
Yeah, so Professor Joel Bregman at Michigan said, to first order, an astrophysicist is a computer programmer. So I don't make such a distinction between the equations on the blackboard and the number crunching. To me, most of the equations that we write on the blackboard that can be solved purely on the blackboard have already been solved. And so everything else needs complicated numerical differential equation solving in order to come to, any sort of interesting answers. So we're just taking those equations on the blackboard and all the physics that we've learned from that, and we're just putting it into the computer and having it generate solutions for us that we can, look at and derive interesting properties from. So I definitely do. I mean, my job is in front of the computer, but I also have pads of paper or, my iPad in which I'm scribbling equations and going, all right, this is the simplest way to express this equation. Now I need to write the code that solves this equation as well. So
Right.
I don't really see a distinction between these things.
Yeah. And so I guess taking a step back from the data science and the data analysis, I think a lot of people, or we saw on your website as well, that you apply for telescope time. So I think a lot of people are going to be interested how you collect the data, and if you like what exactly do you get out of telescope time, or could you possibly be using a mass data set that's already been collected?
Yeah, so it depends on the project that you want to do. The way it works, I don't know if your listeners, viewers know this, but there are many general purpose observatories, and they're designed for anyone to come up with an idea to use them to, do their test, do their experiment. And so you write a proposal for an idea for how to use the telescope, and you ask for a certain amount of time on those telescopes. And it goes to a panel called the Time Allocation Committee, or the TAC, the TAC as we call it. And they look at all the proposals they have, and they determine what are the best proposals, what are the best uses for this instrument with, limited amount of time on it. And the time is divvied up, and then you use the telescope. I'm a multi-wavelength observer, in the sense that many people specialize in one wavelength, so one technique, but I use radio, millimeter, optical, ultraviolet, I do near infrared. I haven't yet done far infrared, though I'm interested in it, and a lot of X-ray observations to study. So I'm sending my proposals out to lots of different types of observatories, and they all operate a little bit differently. The ultraviolet and X-ray observatories, by necessity, because the atmosphere absorbs ultraviolet and X-ray light, these observatories have to be in space. And so for these things, you write the proposal. It goes usually to NASA, which is where most of these things are done, or to a European analog, or Japanese analog, etc. And if you're awarded the time, then sometimes there's a second part of it where you say exactly how you want to use the telescope. Frequently, you have to do it the first time so that they know exactly what they're getting into. And the mission controllers do all of the actual observing to you, and you get an email when your data are ready to be downloaded, and you do it. This is how Hubble Space Telescope also operates. For example, anything in space has to do this. It's just too finicky and too expensive of a thing for anyone to, have their, just anyone to have a joystick and, move this thing around, etc.
Does it ever happen that there's spectacular mistakes and that the controllers just observe completely the wrong thing?
I am not aware of the controllers making a big mistake like that. It is usually vetted through, or it's done through software that has been vetted many, many times. And so you say, I want to look at this object for this amount of time. And when you do it, I want you to move the telescope around this way and that way. And the software says, what will happen to the telescope if I do this. It knows where the sun is, so it knows if you're pointing too close to the sun and so forth. It knows exactly what's going on. So I'm not aware of that. It is totally possible for you to send the wrong coordinates to them, and they correctly observe those wrong coordinates, and then you get back data that is just a very nice, deep stare at an empty patch of sky, which can be frustrating. That has not happened to me yet, knock on wood, but I have heard of it happening to some colleagues of mine.
Mm. And so, for example, so if you never get to go yourself to the observatories, do you, for example, if you have grad students, do you send them there, or is that just never an activity for an astronomer anymore to go to the observatory themselves?
For the smaller observatories, it still is, and even for other things. But they have to be on the ground. We don't get to send anyone to space, and there's no point in sending anyone to NASA just when someone else whose job is that to do that. I'm too old to stay up late at night anymore, so I'm happy to send postdocs, grad students, and other students to the observatory more. I have done it. I think the most recently I've done it was 4 years ago to Magellan Observatory in Chile. But I have students who go do it as well. And, in that case, the bigger telescopes like Magellan Observatory have an operator, and they point the telescope for you, and they're much more attuned to, when the weather is bad, when an instrument is getting warm, and sort of they're much more attuned to what could go wrong, and so they won't move the telescope in a way that will damage it, and they're right there. And your job is just to, tell them where to point it to, and they do it, and then you kind of digitally press the camera expose button and let that come in, and then you're responsible for making sure that everything is calibrated properly in the afternoon, et cetera, and all this, and that your data are worthwhile. For smaller telescopes like the MDM Observatory, which Michigan is a part of, then you're on your own. You are there in the afternoon. The people whose job it is to make sure everything runs properly are there, and you can talk to them. They said, all right, the dewar is filled with liquid nitrogen, it's ready to go. And then you're on your own, and you're actually typing it. You're the operator and the scientist there, turning the telescope. And if something goes wrong, you have to go out into the dome and, troubleshoot, figure out what could possibly be the problem there, etc. And so then it's far more hands-on as well.
And for the purposes of your research, do you find that you often have to go or get telescope time, or is it something that, for example, you can get one session on a telescope once a year, and that'll give you enough data and enough work for the entire year?
It depends on how big that data set is. More data is better. So getting more, the more data you have, the more science you can do with it. So it depends. If I have one really good data set, I can probably write one really good paper on it in a year, and that could be enough. But I also have grad students, and I don't currently have a postdoc, but when I have a postdoc, they also have their research projects to work on. So basically, everyone needs at least one data set to be working on at any given time if they're, an observer. There are, as you said, Thomas, there are archival data sets as well, and that's something I also work on, and so can use those if I don't have any current data on it. But frequently I have a backlog of data to work on, but I always want more to work on as well.
Right. And so I guess the next question is, you see all these different grad students and postdocs and colleagues and other professors working on, research in astrophysics and other topics. Would you say that the current field is moving more towards theoretical or observational, and what kind of direction do you think modern research is going to go?
I think that there's always going to be both. I think, and there always have to be both observational and theoretical astrophysics, and instrumental uh, uh, astrophysicists, people who make the instruments for the telescopes. In other fields of physics, sometimes there's less of a distinction between an instrumentalist and an experimentalist, in that they're one and the same. In astrophysics, there's a clear distinction. Because we're generally making general purpose observatories. There's also sometimes a distinction between a mostly analytical theorist and a numerical theorist, someone who works on code primarily to make numerical simulations.
Mm-hmm.
Although I think that's a distinction without a real difference. It's certainly different approaches, but not a true difference. And there will always be room for all of these moving forward. Because without theorists, there's nothing to test. Without there are no ideas to test. Without observations, there's nothing to explain. So you need both.
Is the Nobel Prize this year in physics having been given out for the study of black holes? Is that going to change? Will that have a direct impact on your work and your research, or is that just a nice thing that happened and then everything moves on as it did before?
It makes me very happy. It's hard to say how that will change things. It is, I think, the positives of the Nobel Prize are that it gets the whole world thinking about science for 1 week at least, and those projects in particular. So I imagine that it could increase the number of people who are interested in black hole astrophysics. Maybe someone was on the fence, deciding between studying exoplanets or black holes, and said, well, maybe black holes is more interesting to me now, and start working on that. I don't know. I don't know if it'll change any funding at all. I'll certainly accept an increased amount of funding for black hole astrophysicists, but we'll see. So, I'm unsure how it'll affect my day-to-day operations or my year-to-year operations directly.
And speaking of other fields of astrophysics and astronomy, it sounds like you've always been interested and somewhat committed to black holes from grad school onwards. Have you ever thought about, for example, changing to studying exoplanets or to study stars, or would that even be possible?
It's certainly possible. I know several people who have really reinvented themselves. I like to moderately reinvent myself as an astrophysicist every 10 years or so, but not completely reinvent. Black holes have just been what interests me, and the fun, the good sides of being in academia are that I get rewarded in studying something I want to study, and so I'm only going to choose what interests me. I have done some projects in cosmology, reionizations, kind of stuff. I'm always interested in expanding my research. But for example, in the last couple of years, I've really started to do more gravitational wave astrophysics stuff right now. But still, although there are many sources that are not black holes that emit gravitational waves, those are still the sources that interest me.
And right. Was that a significant event because I suppose the detection of gravitational waves meant that it added proof to the idea that black holes existed, and it kind of confirmed at least our understanding of what we think is going on in space. But I suppose it just confirmed that. And but you, for example, been working in the field of black holes for a lot longer before that. So did that actually change your field, or was that just so expected and you were so sure that that was going to happen that it didn't change much?
It was a huge deal. Maybe not so much in terms of showing us that black holes existed, because most, everyone already thought that they did. It does paint, any black hole denier into an extremely small corner, in that it would be, theorists can be very creative. So I'm sure there's a theorist who can come up with some explanation for
Right.
the LIGO gravitational wave detections that does not involve a black hole, but it would be something that looks so much like a black hole that I think a philosopher would have a hard time distinguishing these things. So it really shut the door in that case. There were some plausible, there were some speculative ideas before that for what black holes could be other than black holes and still be consistent with the data. And they were not, I don't think any of the theorists proposing them really thought that, these things were balls of neutrinos or anything like that. They're just saying that, I can explain it without, requiring a black hole, for example.
Right.
And now it's, just kind of, very difficult. But the detection was huge in terms of opening up gravitational wave astrophysics, in that there is a project, the LISA, the Laser Interferometer Space Antenna, which is a planned mission to build a LIGO-like detector in space with much longer baseline than LIGO, and so it can detect low frequency gravitational waves. And so LIGO is sensitive to low mass black holes, stellar mass black holes, but LISA will be sensitive to supermassive black holes, on the small side of that. And so I think that LISA, whether it was going to happen or not, was it has been in the works for a long time, but budget cuts meant that NASA sort of pulled out from it, and the Europeans were trying to go by themselves, but it wasn't clear whether they could. But then two things happened. One was the LIGO detection, which really got everyone re-excited about gravitational waves and gravitational wave astrophysics again. And the other thing was the LISA Pathfinder mission, which was a sort of a technology preview for LISA. It was a success beyond, I think, everyone's wildest dreams. And because of that, it was like, oh, the technology is far more doable than we realized. And we're detecting gravitational waves by this kind of method on the ground in a different, different frequency regime. And it kind of, I think those two things together really said, all right, I think LISA will happen. And that's something I'm involved with. I'm on the NASA LISA study team that is, analyzing whether it's a good idea for NASA to, analyzing what would, we're not allowed to make a recommendation by our charge, but analyzing what would happen if NASA were to invest in LISA.
And so what can detecting gravitational waves teach us? Because I do find it's a very cool thing that for hundreds of or thousands of years, our only access to the cosmos was through light and through photons. And now we've just opened up an entirely new kind of just way of looking. It's an entirely new way of seeing, basically. And so what could we hopefully, what do we stand to gain by trying to look in this new, different gravitationally wave-based way?
Yeah, so as we talk about it now, it's multi-messenger astrophysics. So we have photons we're the first one. Neutrinos were also something that were used, but not super accessible, and cosmic rays are another way of doing it. Gravitational waves tell us a whole lot that is very hard to do with electromagnetic astrophysics, and it also tells us a whole lot that's impossible to get from electromagnetic astrophysics. One such example, relatively recently, LIGO detected the merger of two black holes and can tell us the mass of those two things. And after the merger, those two black holes were over 150, approximately 150 solar masses. This is, by essentially any definition, an intermediate mass black hole. So it goes back to my PhD work that, we were trying to say, can you make these intermediate mass black holes? Not everyone was convinced they exist. This is extremely hard to get away from, the fact that an intermediate mass black hole exists. And by golly, it was made by putting two, smaller mass black holes together, which is quite rewarding. So that's one example. There are other things that it can tell you about how frequently supermassive black holes merge for both pulsar timing array gravitational wave detections. That's something I haven't mentioned yet. I'm also a member of NanoGrav, the North American Nanohertz Gravitational Wave Observatory. And this uses pulsars, spinning neutron stars in the galaxy, and they have these very regular periods. And so if you measure this regular period, if a gravitational wave passes through the pulsar or through the Earth, it changes the distance between Earth and the pulsar, and we measure that by change in the time of arrival of this very regular signal. So we can measure even lower frequency gravitational waves as well.
Jeez.
And so on a kind of on a differently related note, completely, all of this stuff that you get to learn, I guess, and that all this stuff that you get to discover, you can only get to it after having spent really a lot of years in school, and by being pretty committed and by working pretty hard and doing all this math and stuff. Was there ever a point when you were going through either college or grad school that you thought, this is too much, this is maybe not from, did you ever feel that this was just not the career path for you because it was just being too much, and so you thought you might change, or were you always dead set and you just kept plowing forward?
This was always the number one goal, but there were definitely times where the grind really got to me. In undergrad, less so, because once you declare a major, and after a year or two, it becomes hard to declare a major. And majoring in physics, there's a lot of stuff you can do with it. So I could have gotten my bachelor's in physics and done whatever I wanted after that, in reason. And so there was a time when I was like, I don't know if this is what I want to do. Maybe I just, maybe I want to become a doctor, or maybe I want to do something different. But once I did the undergraduate research with David Kerner, it just reignited my love for science. And it's just like, if I stayed up late, not because I had to, but because I loved doing it, because I got, obsessed with solving the whatever problem I was working on, and liked it so much. And so realized that actually, no, this is something that I enjoy doing so much, and so I can continue with it. In grad school, it happens again. It's grad school is hard work, and not every day is sunshine and lollipops. There are times when a problem set really kicks you in the butt, and there's a time when your code's not working, and you've spent a week trying to solve it, or worse yet, you've been using it for a year, and then you discover a problem in the code that had been there all along. And there, there are tough times. And once I started working on black holes again, it really just, again was, I enjoy the process, I enjoy learning this stuff so much that it's just fun again, and I'm happy to keep doing it.
And how did you cross, or how do you deal with, I guess, the line that separates learning stuff that people already know and then doing actual research? Because, for example, I do in my undergrad research, which has also been one of the biggest ego checks in my life, because you think that you know something and then you actually really don't. And you have to go away and learn something that exists already in textbook. But I assume, and I've heard this from several people, that feeling that there's always more stuff to learn that you should be doing before you actually start doing, I guess, quote unquote, research never really goes away. I assume that even as a professor, there's always more math, more something that you could be learning that's already been done. So how would you at some point make a decision and say, okay, I know enough about this, I'm going to focus on research now?
So grad school, especially in the US system, is set up for you to work as an apprentice in research, as alongside your classwork. So in the first couple of years, you do, I don't know what the fraction is, but you do some classwork and some research. And after you are done with all the classes that you have are required to take, then all you have left to do is research. And that involves reading papers that other people have written. And so in that sense, you're learning stuff that is still new to you. Even if it's not being taught in the classroom, you're still learning that, and you are applying tools and things that you've learned in other regimes to a brand new problem, and creating that information and knowledge for other people to learn in your papers. So the high level research is not super you're creating the information and sharing it with others, and when others share it with you, you're learning about that as well. And just because it is not in a textbook or not a directed study doesn't mean you're not learning new stuff. I am and the way I operate is frequently by looking at statistical methods that other people aren't looking at or thought about in an astrophysics context, and saying, oh, I wonder if I can apply that to our data sets and see what happens there. So there's a lot of new learning to be done, even when I'm reading 1960s statistics papers that are completely new to me, even if they are not to the statistics community, for example.
Do you ever find it frustrating that you never seem to get to the bottom line, that answers are never final? Because, for example, one of the reasons why I decided to study physics in college was because I thought, oh, there's all this cool stuff that I want to know more about. And now that I'm here, I realize, oh my God, there's even more stuff that I don't know about. And I find that a little bit frustrating at times. Do you find that frustrating in your career, that there's all this stuff and there's all these open questions and you can't possibly get to the bottom of all of them?
I call that job security, knowing that there are always going to be scientific questions that need to be answered. I hope I've answered some, and I hope to answer more. It's just like, I think a poet doesn't think there's an ultimate poem to be written, that there's more poetry to be written. There's more science to be learned, more science to be done.
And so
I guess,
go for it.
Oh no, I was gonna ask, with all these discoveries, which discovery are you most proud of? Because we noticed on your website there's a large plethora of papers. So which one are you most proud of, and which big unsolved question left do you want to solve the most?
So Picking my favorite paper project is sort of like picking my favorite child. They're all wonderful in their own ways. Um, I I'm not going to pick a favorite in that sense. You
Hmm.
know, they're all at different parts of my life. Like looking through a photo album, you know, you have friends from along the way. They're all special in their unique way. Looking forward, what I'm really
Hmm.
interested in is trying to find electromagnetic counterparts to gravitational wave signals. I mean, there obviously has been one with the kilonova, but I'm interested in it for supermassive black holes. So what can we learn? Can we make predictions for what merging supermassive black holes will look like in X-ray or optical light, for example, that would, when they are also emitting gravitational waves, or when they will soon emit gravitational waves, or um, shortly after they've emitted gravitational waves. So a lot of people are working on this. A lot of different answers on what the right thing, right way to do this is. So that it's been my focus right now.
And so what would you then say that your day-to-day life as a professor looks like? Because surely not all of it is spent just in your own bubble thinking about complicated problems. There must be a lot of things that have to be done, and you have grad students and all of that. So would you typically, how does the professor who studies black holes spend their day?
Uh, there are well, so first of all, I teach. That is, uh, I teach Astro 201 that you guys took with me, and I'm still teaching that. I'm teaching that this semester. So that is part of it. So part of my day is, 3 hours a week is lecturing. There is a fair amount of preparing those lectures beforehand. Uh, and then there's also the other stuff like preparing problem sets, homeworks. There's a midterm I'm giving next week. I have to write that as well. So that, and then um, having office hours and talking with students about learning this
Hmm.
stuff, and meeting with the GSIs as well. It's kind of it's sort of like a a stage production of a play that you put on multiple times per week. You have to keep this machine running smoothly as well, and there are a lot of parts to that. uh, Additionally, there are responsibilities to the department to make sure the department is doing things properly. We're an office just like any other office, and so we have concerns about human beings being in the same place with each other. And so, for example, this semester
Hmm.
I am a faculty representative on the Diversity, Equity, and Inclusion Committee, and so I attend meetings for that with the other DEI committee members. It's an open meeting, and I also represent the faculty in this, and so raise concerns and make sure everything um, uh, is working well there. I'm also involved in admitting grad students to the program. That's also something I'm involved with. And then I meet with other people. I have telecons multiple times per week, per day, um, in which I talk with other people, involved with the NASA LISA study team, other people on the nanograv experiment team about what I'm working on, what other people are working on, what we should work on next, etc., uh, to push that forward. And then I get to work with my grad students. I have weekly meetings with my grad students. Um, I have a weekly project meeting with the undergrads doing research with me, and a weekly group meeting that everyone comes together for. And I'm also working with a high school student in Turkey doing one project as well. And so I have weekly meetings with him. in between all
That's
those
quite a
times,
lot.
yeah, so in between all
Yeah.
those times is when I get to do my research. And when I have students working with me that I can say, all right, I have this good idea, you have more time than I do this, and then we'll meet back next week and we'll talk about how it goes. And if you have any problems, I can help troubleshoot, and then we'll move forward with that. But there are things that I want to do myself. So, for example, this week I finalized a reply to a referee report on a paper, and send it out to collaborators, and we'll take in their comments and then resubmit it to the journal as well. I've also am working on another project. I have been drafting a very long email for longer than I care to admit about where another project is in terms of what collaborator and I have been doing, and asking the other collaborators their opinions on, we have these two results. Do we believe one more than the other? Why? Or should we just, say that there are positives and negatives to both of these, and we should put both of them in the paper? And so that's kind of that thing. And there's a lot of time spent, yelling at the computer saying, why aren't you, doing what I want you to do, and so forth, and getting things to come out of it as well. So that is what my sort of weekly kind of thing is like.
And on top of all of that, has coronavirus changed a lot in your routine? Obviously, beyond the fact that many people now have to work at home and there's the very real disease out there, but on top of that, has coronavirus affected observation and research and things like that, or have you guys been able to kind of sail over it?
So we're lucky in the sense that my work is done in front of a computer. So in that sense, my job is still able to be done while at home with a strong internet connection. Many observatories have been closed for quite a long time because you have to have people there to run the machines and such. Most of my stuff is done through these space observatories, which have been kept running, thankfully. So that has not impacted my research so much. Other people have not been able to get data from the ground observatories where they need, to travel to, and it is not allowed by the university to fly for business purposes for some period of time. I think you're allowed to in some circumstances now, and but I don't want to. Even if I were allowed to, I don't know whether I'm allowed to because I don't want to. So in that sense, there are other things where giving talks and going to other departments and giving talks and meeting with the people there. So, for example, I had a number of such planned visits that were canceled and now have been rescheduled for online talks. And the online talks are okay, but what I miss is that, you go there and you have nothing else to do but be present in that department then.
Right.
And so you can, interact with people there that you wouldn't have interacted with otherwise. And that sort of gets curtailed a little bit in these virtual meetings, unfortunately.
And so I think probably one of the last things that we thought of to talk to you about is what do you think has been, or what do you think will be the biggest thing that understanding black holes can bring to a better understanding of science? What do you hope is the ultimate end goal of studying black holes?
Wow. So it's not something I directly study, but a lot of quantum gravity theories use black holes as sort of theoretical thought experiment testing grounds for things, because black holes are an extreme of general relativity, and our understanding of the quantum realm is complete except for gravity. And so you kind of put these two theories together. We know they're incompatible right now, but will string theory work and combine these things? So I think this is one place where black holes are useful theoretically for helping to understand what's going on there.
Awesome. Thank you. Oh, go for it.
Yeah, I was just gonna say, just to wrap up on a lighter note, what are other things that you like to do besides astrophysics? Like, what would you do in your free time?
Pre-coronavirus, so first of all, I have a family, so I spend time with my family a lot. I have two hobbies basically. One is I watch soccer. I support a couple of football clubs.
Which ones?
Locally, I support DCFC, Detroit City Football Club. In the Premier League, I support Tottenham Hotspur. And so that's, one thing I do. The other thing is I do endurance sports, mostly triathlons and marathons. But so I train for them as a way of getting exercise and, really exhausting my body as much as possible.
Which does also dispel the myth that all scientists are just nerds who wear lab coats all the time. Not that we've ever seen you wear a lab coat. Awesome. Well, thank you so much for talking to us, and thank you for being on our podcast. That was very interesting and enlightening.
Awesome.
Thank you. This was quite a pleasure chatting with you guys.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.